I believe that what I'm talking to you in this talk should come as an evidence to most of you, if not all. And it is that we have these two amazing instruments at the Cassegrain focus of the CFHT, espadons and Spirou. And why not making them work together? So is this moving on its own, or can I move it somehow?
You can do it.
Okay, thank you.
Sorry, that was me.
So anyway, so this is what Vision is all about, to try to make these two spectropolarimetries work together. And if the word polarimeter was not in the name of these instruments, this talk would be very short. I mean, you just actually put a couple of mirrors, redirect the light into one or the other instrument, a little as a problem of mechanics, job done, talk finished. But polarimeter is in there, and that's the reason I'm here, because polarimetry is a problem. So how you can redirect the light and still keep the polarimetry. So please give me just a few seconds of math. Don't get scared. And I think you can get the basics of how what the problem is and how Vision works. This matrix over there describes what happens to polarization when it goes over a mirror, when it goes over a reflection. If nothing happened, this matrix will be a diagonal. The first row describes what happens to intensity. The second and third rows describe what happens to linear polarization. The last row describes what happens to circular polarization. And if you look at it, you get this number 1 minus q squared, which is not zero. And that means that after reflection, whatever you had as linear polarization, you will end up with linear polarization. A reflection will polarize light. And it's not the only thing that happens. Look at this bottom part of the matrix. It's not diagonal. It means that circular and linear polarization will get mixed up after reflection. So mixing up polarization, introducing linear polarization, any or the other is a bad thing for an instrument that measures polarization with such a high sensitivity as espadon and Spirou. So what to do? Well, the good thing about this matrix is that it's highly symmetric. You look at the top or at the bottom, you see that things are the same, just a change of sign. So the idea should come to your mind that perhaps you can build up the inverse of this matrix. And actually it's quite easy. It is sufficient to rotate the matrix 90 degrees to get exactly the inverse. So if this matrix gets multiplied by itself rotated, you get the identity and the problem is solved. So how do you rotate the matrix? Well, good thing is that you just rotate the matrix by rotating the mirror. So here you have a scheme. Light is coming vertically from the telescope. It goes 40 degrees from the first mirror. You corrupt polarization, but then you go into the second mirror that reflects light out of the screen, and its Miller matrix is exactly the inverse of the first one. The light that gets out of the screen has exactly the same polarization as the one that came in. And this is the way to go. You just need to plug in two reflections like that, rotating 90 degrees, and you will not corrupt polarization. And this is what Vision is all about. Now, this is the perfect world, and the world is not perfect. For this to work, these two matrices have to be rigorously identical, and they never are. The mirrors have to be exactly the same, perhaps they are, but the angle of incidence have to be exactly the same. And you have opticians making non-collimated beams. So every one of these rays has its own angle of incidence on the mirror and a second angle of incidence on the second mirror. So the two matrices are not identical. Vision does not work. So, well, the world is not perfect, but we are going to do our best. Perhaps we cannot get the identity, but we can get something that is sufficiently near to the identity to work. So this matrix should be, as I said, the identity. It is not, but if you get all these numbers, not zero, but small enough, you can do all the science of espadon and Spirou with corrupted polarimetry, but the polarization that you get corrupted will be below noise. So you can do all the science. So this is what we want. We are not going to have a perfect system, but it's going to be perfect enough for our necessities. How can we get that? Well, first thing is reduce the angle of incidence. This will help you. The smaller the angle of incidence, the smaller the problem. So we figure out for the CFHT that 12 degrees would do it. Why 12 and not 5? Well, unfortunately, the two polarimeters are made out of fermions, and fermions do not want to share their state, their quantum state, so they don't want to be one on top of each other. Mechanical engineers have another way of saying this, but at the end is that it's a problem with fermions. If they were bosonic polarimeters, we could do it better. Anyway, so 12 degrees is the smaller angle that you can get both fermions and mechanical engineers happy. And that's it. We are going to put 12 degrees. Can we do a good crosstalk matrix with 12 degrees? Well, let's look now at what we propose for vision. We propose 3 modes. In the first one, light goes through into Espiro, nothing to worry about. In the second one, light gets reflected by a mirror and goes into Espadon, and we are going to look at this. With mirrors, can we do it? We picked silver mirrors, and this is again this Muller matrix, 4 times 4, 16, but this time, instead of just one number, I'm putting one number per wavelength, so we can cover the full spectral region of Espadon. The crosstalks that I don't want to pass are given by the red lines. So in summary, every time the blue line is inside the red lines, we are in business. And you see that with mirrors, well, perhaps there is a little problem here on the blue end of the spectrum, but I made this matrix actually, the optical engineer made this matrix with a misalignment. The mirrors are not exactly at position, they are slightly misaligned. So even if we misalign the mirrors mechanically, we are still in business for mirrors. Can we do it simultaneously? That means working with dichroics that split the light, send the visible light into Espadon, send the infrared into Espiro. Well, dichroics are nasty beasts made of plenty of layers of who knows what made of. So it's not so easy. So we had some experience at PICDMD with them. So we tried to apply that experience to the CFHT, and we asked for a first proposal from our industrial partner. So what I'm showing to you is just the first proposal. We got some money to make a study. The study has just started, and this is the starting point. So this is for Espadon in reflection. Every time the blue line goes above the red line, we have a problem. And you see that there are a few points in which I go above the red line. So that means that we still have problems, but there are very few. I think I could be ready to fight that even in this state, it would be worth using vision. But we are just starting this study. This is just the first matrix that they proposed, and we are now need to work. And I'm very optimistic that all these blue peaks are going above the red lines and going to go below the red lines in the near future. So I think we should be optimistic about that. This is vision. This is Espadon in reflection. What happens in transmission? Well, things are even better. And it's a good thing that this thing is here, so you cannot see the problem there. But as you go to the 1 micron region, you get a few points in which there is a problem. Again, this is just the first step. We have not yet started our study. I'm very confident that this is going to disappear as a problem very soon, and that we are going to get most, if not all, of the spectral domains of both Espiro and Espadon inside the red lines, and this is going to work. So, with all these optimistic notes, the mechanical engineers figured out how to put the 2 instruments together. The image is better there. So what you get is Espiro in the vertical, Espadon on this angle when the telescope is looking upwards, and we substitute everything which is behind the bonnet in the Cassegrain by these new mechanics. If you look inside the mechanics, you find this piece on a sliding mount. It has, when it is all the way to the right, you go light going into Espiro as alone. Then you can put just 2 mirrors, and then light goes into, vertical light goes into Espiro. If you put the mirrors, it goes into Espadon. If you put the dichroics, you go to the both of them simultaneously. Just by moving this small piece inside a motor, you can go from one instrument to the other, which I think is kind of eye-opening in the sense that what can you do with this? So this is just the first design. It's not probably going to be the last design, but it's just where we started working. And it allowed us to say how much it cost. So let's go very fast over this. 150 kilo euro. We don't have them, please. Ideas. Maybe I should go back with my hat, getting money, but anyway, just joking. There are very good propositions around to get this 150,000, but we still don't have the money. So this is one of the things that we maybe want to discuss in the next days. Going to more interesting things. Well, I think that for most users of espadons and SPRU, it should be obvious what having the two instruments together should bring us advantage. I wanted to put forward a few things that, well, I think they're obvious. The two instruments are mounted simultaneously on the same mount, so they are very stable. They are very stable for measuring velocities, but they are also very stable in front of accidents when you are mounted or dismounted. Ease of operation for the technical team. You can go from one to the other during the night. And if they work together, you get a nice instrument go from the near UV all the way through the thermal infrared, doing very sensitive spectropolarimetry at high resolution. So what science can you do with that? Well, you let me know. But we put together a document trying to explore a few of those cases that you can consult. I'm a solar physicist, so I'm here out of my terrain. So everything that happens after sunset, I'm familiar with. But I took two examples that I think are important, or I was told are important. For exoplanets, you have all those lines in the visible and in the infrared. You measure velocities in the infrared, you get all those visible lines to detect stellar activity, so you cannot detect false exoplanets. I think that's a good thing to say. Magnetized star and planet formation. Again, the same thing. You can measure Zeeman broadening in the infrared, circular polarization magnetic fields on the visible. One gives you large-scale magnetic fields, the other gives you localized magnetic fields. I think there's a good deal of new science to be done with this simultaneous instrument. But, and this is to end my talk, if you allow me, I'm going to make a little propaganda of myself. So I used my own field of study after sunset, I mean. What I'm showing you here are some of the first three-dimensional images of Betelgeuse made with neural bulb, but we are doing them with espadons as well on Antares. Let me say it again, because maybe it's not clear. These are images. These are not simulations. These are not numerical simulations. These are images. These are not cartoons. These are images. I hope this is clear by now. 3D images. We do it thanks to measuring linear polarization in the atomic spectra of Betelgeuse. At the right, you get what we believe is the right spatial scale. At the left, I stretched everything times 10, so you can see the hot plasma, the hot convective plasma going outwards and expanding. And now you wonder, what kind of magnetic fields can you get out of these flows? Well, it's good. It's a good thing that we have these nice spectropolarimeters to measure magnetic fields, so let's do it. So here you have a video, you have the date, the calendar day moving on the top of, we have been observing Betelgeuse since 2013, so we can make images. That's the brightness of the image of Betelgeuse. These are the velocities we measure. You can see the convective flows, and this is the magnetic field. And you maybe, if you look here, you can see some blue and red, but the image is mostly white. Why? Because Betelgeuse is very red, and the fields are extremely weak. So espadon is barely able to get any signal. What you need here is a SPIRU. But if I use a SPIRU, maybe I can get magnetic fields here, but I will not get the images here. So yes, I need vision. I need vision to fill up the magnetic fields here and still get the images here. And with this, I'm ready for questions if you have any. Thank you.
Thank you, Arturo. So was that a simulation or was that?
No. Did I say that?
Was that images? Is there any question? Yes, Rodrigo.
I was just wondering, would it make it easier if you just, I mean, if you did both, but just kept the polarimetry part for one of the instruments?
Sorry?
I mean, if you did polarimetry on either SPIRU or espadon, but not on both, does that make it easier to
You mean just one and then the other? It's a possibility, but if the dichroics work, why you would not do it?
No, I was wondering if it made it easier.
Actually, because the dichroics are so critical to the project, we imagine this possibility of having either one or the other with a rapid switch between the two, just in case dichroics do not work as expected. Today, I'm very optimistic, but the reason for these two modes at the beginning was exactly that at least we can get one and then the other then in rapid switch. But since dichroics work, my bet is that if the dichroics work, nobody will ever use the other two modes.
I don't see any question online. So just before wrapping up, before going to the discussion, I want to say that it's really nice to see that we had a discussion 3 years ago at the last users meeting about doing that and whether that was needed and so on. And it's nice to see how it's evolved into a proper concept. So thank you very much for this.